Today I will talk about bose-einstein condensate and quantum information. So, when we talk about BEC or bose-einstein condensate, first we have to know what is the contribution of Bose and Einstein in this field. So, let us just see that what is the theoretical background of this field. So, this is the invention in 1925 by Bose and Einstein jointly, and they have invented and theoretically predicted bose-einstein condensate. So, but why this field right now is so emergent field after so many years? So, that is the reason that in 1995, after almost 70 years, these people like Cornell, Wyman and Ketterle, they have first realized this system in experiments. And that was quite non-trivial experiments, and that's why it took almost 70 years to do it. And that is the reason that it attracted Nobel Prize in Physics in 2001. And according to Pitowsky, this discovery must be viewed as one of the most beautiful physics experiments of the 20th century. So, now onwards, my talk will be like, first of all, I will start like how I want to view, I love to view the bose-einstein condensate. So, I will smoothly transit from the basics of the BEC to the very advanced and the recent activities in this area. So, let us first see that how it evolved. So, this is the Blackbody radiation spectrum, which is quite well known, and this is the starting point of quantum theory. And this is not only the starting point of quantum theory, this has a lot of importance for the discovery of BEC. I will come slowly that how it evolves. And this depicts the Blackbody radiation spectrum. So, we know that any heated body, it emits electromagnetic radiations, and it was found experimentally that it depends on the frequency in this fashion. So, it was observed that when we change the temperature of a body, that emitted radiation changes in frequencies. So, when it is like if we heat a iron rod, and then it emits some infrared radiations in couple of hundreds degree centigrade temperature, but when it turns to the red color when we heat it around 1000 degrees Celsius. So, that is why this frequency is shifting towards right, and this is the trajectory it is having in the experiments. Now, lot of attempts has been in the literature to model these systems theoretically. So, first that I would like to mention about the Wien's law, which is the distributions of Wien's, which is the basically the combination of displacement law and the distributions in the classical physics based on the thermodynamics. So, this distribution law, basically this is matching in the higher frequency regime. This is clear from this plot. In the last moment I have drawn in PowerPoint, so it's not very accurate. So, but this is Wien's law, which is matching with this plot in the higher frequency side. And then Rayleigh came and he thought that let us model it like the Blackbody spectrum is composed of infinite number of harmonic oscillators, and these harmonic oscillators are having the average energy which is kT. So, in that point of view, he has calculated this assuming the harmonic confinement and number of states in a given energy interval. So, he has found this expression, and which is matching in the lower frequency regime. You can see this is the Rayleigh's law, and this is not matching in the higher frequency side, and this is also in other language this is called the ultraviolet catastrophe, because in the higher frequency in the ultraviolet regime this is not matching at all. Okay. So, when Planck came, Planck was overviewing all the things which is existing in literature. So, he thought that let us think the system in some other way. So, let us think the system or the radiations is composed of not a classical oscillator, instead of that some oscillator which is having a discrete energy spectrum, and this discrete energy spectrum is having this oscillator is having the energy which is a multiple of this quantity h and nu. So, h is the Planck's constant and nu is the frequency. So, any harmonic oscillator will have the energy in this quantized form, and in this way he calculated this density of states and then found the distribution law, which is this. And after finding this, if one sees and plots this is almost exactly matching with the experimental plot of Blackbody radiations. And this was quite remarkable step, and this is the origin of quantum theory, and this is the first time the quantization has come into the literature. So this is the way that Blackbody radiation spectrum was matched in this way in the classical analogy. But I would like to say that after that also many scientists have tried in their way to prove and to model this system, Blackbody radiation, and this is the step of Einstein. So he has basically modeled the atoms and the system of atoms and photons. So the atoms are modeled by two-level systems. So basically this is possible in experiments. And we know that there are three processes, main processes involved in two-level systems. One is spontaneous emission, and when the atoms are in the excited state and it comes down to the ground state spontaneously. And this is stimulated emission. When we have the field present in the system, then we have the emission which is of the another photon in addition, but the atom comes down from the higher state to lower state. And this is absorption which happens if we apply some field from outside and the atom excites to the higher state. So this is the process considered by Einstein in the two-level system, and this is the basically explanation of Einstein in this system, that this A21 is the probability of transitions of this spontaneous emission from the second level to first level, and the probability of transitions of stimulated emission is B21 and the other one is B12. So these are called the Einstein AB coefficients, which is well known in quantum optics. So but what we want to emphasize here is he has related these with the energy density in the conditions that if you have the equilibrium of photon and atoms in the systems, like the atoms in the higher state and the number of photons, this is conserved, then in equilibrium you have the relations with the density of the higher state and density of the lower state and the Einstein constants. So using these relations, he has obtained the energy density of the system in this form. But here one has to think that we do not know so far that what is A21, B21 and the other coefficients. Although we may have the information of N1 and N2 for the particular level, but we do not have the information of these coefficients. So then Einstein used this distributions law, which is MB distributions law, which happens for any normal temperature between the levels, the occupation between the levels, and then he has transferred it there. But he did not know how to find these coefficients in reality in experiments. So he could not, although he wanted to derive Planck's law, but he could not do it in this exactly. So what he did, he forced matching the Planck formula by taking that B12 and B21 is equal, and then A21 and B21 is this factor. So this is related to frequency and this is by matching this formula with the Planck's formula. So this is not an independent foolproof derivations of Einstein. So he did not or he could not prove this theory of Planck by using the two-level approximation, and also he did not know the concept of indistinguishability in the year of 1916. So this is the step taken by Einstein, but then what is the next step? Then Bose came, and he has the information of quantizations by Planck, and also he was inspired by Compton's discovery by saying that this energy of the photons and the momentum is given by h nu by c. So he computed the density of states and the frequency between frequency nu and nu plus d nu, and by evaluating that he has found the for photon gas this is the expression of the number of photons in this frequency interval, and which is exactly matching with the Planck formula except some two factor. So he assumed the photon to be indistinguishable and any number of photons can be accommodated in a single state. So this is the step he has taken, and since the radiation can have two states of polarization, I mentioned that there was a factor 2 lagging in the expression. If you compare with the Planck's expression, then this can be found by the physical scenario that we have a two states of polarization and then it is multiplied by 2, and then he found the exact expressions of what obtained by Planck's law, and it is matching with that. So he has written some manuscript which is Planck's law in the hypothesis of light quanta, and he sent it to Einstein, and Einstein immediately realized that this is a remarkable work, and is a big step towards the quantum statistics. So immediately he translated and got it published in the journal. This was the bold steps taken by Bose, and the particles are distinguishable. Their number was not conserved because this is photon, we are talking about photons so far, and they have the spin 1. So by these 3 bold steps he could derive Planck's law and thereby laid the foundation of quantum statistics. So this was the origin of quantum statistics, and I will tell you how this is very strongly connected to the Bose-Einstein condensate in my next few slides. So let us see that what Einstein did after that. After this work of Bose, Einstein generalized this for the massive particle. So he said that this is not only true for photon, this is also true for massive particle like atoms. So and then for atoms he has to take the total number of atoms, it is fixed, is constant. Then atoms are completely free and do not attract and repel each other. So you do not have any interaction between the atoms for this system. And then he generalized and he introduced the chemical potential here, and this is the distribution function which we call Bose and Einstein statistical distribution function is evolved like this, and this is the fugacity and chemical potential, and for bosons it is this term is from 0 to 1. So this is now we have arrived to Bose-Einstein statistics, and basically I am mentioning the line of thought how this BEC is involved in this way. So this is the derivation of B distributions in the statistical way by expanding, and in number of combinations should be taken in the Ni particles in GI degeneracy, and then Stirling formula and all, and then you can arrive. So after obtaining this Bose distribution, so what is the aspect of this distribution which we need for BEC? So let us see that, let us give the simplest example, that we have 2 particles, 1 and particle 2, and we have 2 states, quantum states, state A and state B. So the first case the particle 1 is in state A, and the second case the particle is in state B. And the other case I will take another choice, that the second particle goes to state A and the first particle goes to state B. In the first case the quantum state can be written as the product of phi 1a and phi 2b. This is the particle and AB are the states. So this is the wave function of particle 1 and this is the wave function of particle 2 in state A and B. And the other case it is phi 2 1 is the other combination. So now let me tell you that if this is a Hamiltonian remains unchanged because the particle are interchanged. If you change particle from 1 to 2 and 2 to 1, because the particles are similar particles, so you have to have the Hamiltonian same. And in this way, you can see that both the wave functions are simultaneous eigenfunction of this Hamiltonian. So the general wave function of this system would be a linear combination of both of them. So we have psi 1 2 is this, and psi 2 1 is the other combination. The phi 2 1 goes to the other place. So now this probability should be conserved, and if you see that 2 wave functions will have the conservation of probability, then you will have the relation between the coefficients, which is A is plus minus of B. So now we have 2 combinations, one is A is plus B and A is minus B. So we have this linear combination of the wave function, which is phi 1 2 plus phi 2 1 and phi 1 2 minus of phi 2 1. So we have a symmetric state. If we change 1 and 2, the particle 1 to 2 and 2 to 1, we swap the particle, then this wave function remains same, and this is the symmetric wave function, and this kind of particle is called the boson. Okay, and this is the another combination, which is the negative sign. If you change the particle, swap the particle, it gives a negative sign in front, and so this is the antisymmetric wave function. We call it fermions. So and another aspect that it is not only the definition. Now I assume that the state A and B, this is the important step, that state A and B both are same quantum state. So what happens if A and B are same? So if A and B are same, you have that phi 1 2 and phi 2 1 both are same. Okay, and then you have a non-zero symmetric wave function, but you have a zero wave function for the asymmetric case for fermions. So if the 2 states are same, so for example, if I want to keep more number of atoms in a single quantum state in the same state, so it is possible for bosons, but this is not possible for fermions. So that is how this is the basics basic of what we call the Pauli exclusion principle. And so bosons do not obey Pauli exclusion principle, and we can number of atoms, a large number of atoms are allowed to be in a single quantum state. So that is the essence we need from these statistics, and this is the origin of that. So let us see that after seeing that what the aspect we need, what is the conclusion we need from the Bose statistics, and this is in high temperature limit of the statistics. What happens at high temperature? So this is GI Ni. This is the symbol is not here. This is very less than the energy, and so particle are distributed over a wide energy range. So in high temperature, if you see the Bose distributions here, so you see that the mean is negligible compared to the energy, and then you can this part is very high compared to 1. Then 1 basically arrives at the Maxwell-Boltzmann distribution, classical distribution, which is exponential minus of this. And so this is for high temperature. So what happens at low temperature? At low temperature, you will have the chemical potential in rising with the temperature. It is because that if the chemical potential is like you want to add some atoms in the system, and then for that you have to lower the system more and more. So that's why you have to have chemical potential more. It will be increasing, but it cannot cross the minimum amount of energy in the system, available energy in the system. So when it arrives at mu equals to the energy value, minimum energy value, then the number of, you see that distributions here again, that it blows up. This distribution function is having very large values, contributions in the number of atoms. So one basically can have the number of particles in single particle ground state becomes arbitrarily large. So now we know that by starting from these distributions, how we can arrive at the point that number of particles in a single quantum state can be arbitrarily large. So we can put in principle large number of atoms in the system in the particular quantum state, which is the minimum state available of the system. And after these conclusions, I want to say that this is the, at low temperature, this is the concluding sentence. At low temperature, significant proportion of atoms in a gas condensate in a state of lowest energy of the system, and this is nothing but Bose-Einstein condensation. So this is the definition, how I love to see Bose-Einstein condensate, starting from very basics, and then this is the condensation occurs in momentum space, not in coordinate space, because so far we have not used any spatial confinement. So far it is a free system. So the condensation, if you take the temperature very low, where this chemical potential is equivalent to the minimum energy values, there you have the momentum is almost 0. So you have the condensation is momentum space, not in coordinate space, and the condensation is purely of quantum origin. So this is a purely quantum system where so far the condensation can be in momentum origin. So this is the physical, what is happening in the system in the large temperature. Is a high temperature, the atoms of the gas is moving randomly in the system, and that is well studied in the, it is not very difficult to study this system. And then if one lowers the temperature, then these atoms, de Broglie wavelength gets larger because of this relation. If you lower the temperature, de Broglie wavelength becomes larger, and then they are behaving like a mini wave packet. And then at critical temperature, if you lower the temperature more and more, there will be some critical temperature where these de Broglie wavelength will start overlapping each other. Okay, and that is the point of Bose-Einstein condensate. So we can see it from the Bose-Einstein statistics. We can see from the what is happening exactly in the system if you lower the temperature of this gaseous system. So when they start overlapping, this is the critical temperature we call when the de Broglie wavelength is equal to the interparticle spacing. We have two particles, de Broglie wavelength, they are overlapping, so their distance are equal. So, but if we ideally lower the temperature and take it to the absolute zero temperature, ideally all the wave functions, all the de Broglie wavelength, they will overlap, they will combine to form a single wave packet, and that is nothing but the wave function of the condensate, and we call it a giant matter wave. Okay, so this is the physical basic explanation of how what is happening in the system. So I would like to mention that how this atoms population changes with temperature. At below the critical temperature, now onwards we will be talking about the systems below the critical temperature, and here is the condensate fraction, the plot of the condensate fraction with temperature. So it is scaled by the critical temperature. So when it is 1, it takes the value 1, and then if you lower the temperature, and this is the occupation of the ground state, so minimum energy state of the system, and this is the occupation of the excited state. So if you lower the temperature, after this point the occupation of the ground state suddenly rises up and goes to 1 at absolute 0, what we found from the physical point of view. So this is exactly is the theoretical calculations can be obtained from the basic principle, and one can get the expression of this kind, which is the ground state fraction. This is the total number of atoms, and T by Tc, when you take this is alpha is some parameter which is dependent on the trap. Like if you have to have the system in the reality, you have to confine in some place. So that is the factor which is responsible for this parameter alpha. So this is for some 3-dimensional harmonic confinement. We have just taken some value of this, and this constant n lambda cube, this is normally in popular language is called the gas constant, and this is very important in this system, because when n lambda cube is in the order of 1 or more than 1, we say that the system enters into the quantum regime. Okay, and this is in 3-dimensional harmonic confinement, it value comes out as more than 2.5. So it is a purely quantum system, and this is the condensate fraction we are getting from the theoretical calculation. So this is the thing which is at finite temperature, and then we get a number of atoms, large number of atoms in the ground state or the minimum available state in the system, which is BC. And here are some of the parameters just to get an idea that these atoms occupy identical single particle quantum level, and this is de Broglie matter wave is comparable to the interparticle spacing, which is the order parameter, and temperature is in the order of nanokelvin. It's a very low temperature like 40 nanokelvin, 50 nanokelvin. That is the more or less the usual value of the critical temperature, and number of atoms can be up to this, and then lifetime can be, it varies from various range, and recently it has come few minutes even, and particle density is like this. Size is in the range of the micrometer, or normally 50 or 100 micrometer is the normal range of BC. And these are the atoms, alkali metal atoms, which is already experimentally they have observed BC so far. In my knowledge, rubidium, sodium and lithium, these are the 3 elements which is obtained in the first in 1995 by the 3 groups, separate groups. So, okay. So after saying this, I just give the glimpse of this, how these things are done. So this is just some summary of the calculations, which is density of states, and then for different kind of confinement. Just now I mentioned that we have to confine the system, otherwise we cannot observe in experiments. So this is the 3-dimensional rigid box, and then alpha is 3 by 2, and 3D harmonic oscillator, which is alpha 3, and then one can calculate the parameters with this kind of density of states, and then one arrives at the critical temperature. So one can exactly calculate what is the value of the critical temperature if you know what kind of physical systems it is considering. So okay, so let us see that so far I have given more or less the basics of the theoretical side, and as I mentioned that after many years the experiment is done recently in 1995. So I would like to, although I am theoretical physicist, but I would like to give the physics of the experiment, what is going on, because this is very remarkable experiments in this field. And this already I have mentioned, this Cornell was a postdoc at the time when they have invented this thing experimentally, and the main hurdles was the cooling of the system towards the nanokelvin temperature, and that was basically Cornell has come up with the idea of evaporating cooling. I will come to the point in more detail, and Cornell and Wyman, they have done they have realized BEC in rubidium atoms, and Ketterle has done for sodium atoms. So let us see that what are the main steps involved in the experiment. This is the technique used. Well, the first step is the laser cooling, which is it becomes very popular after this invention of this cooling. A lot of systems have got benefited out of it, and it utilizes the Doppler shift, and it also attracted Nobel Prize in 97. And then the next step is the laser and magnetic trap. So system has to be trapped, to observe it, and also if you want to cool it, then you have to focus the laser, you have to focus the magnetic field at some point, so you have to confine the system first, and then you can have the evaporating cooling, which is the main part which was not sorted out before this time. And this is the basically schematic diagrams of the trap. You can see that this oppositely rotating magnetic field is there is a magnetic field generated which is highly inhomogeneous magnetic field, and the lasers are coming from the 6 directions. So like that the atoms are trapped in the middle, and then this is the experiments by Ketali lab. I could not take the picture as a whole because it's a very big optical bench and is very difficult to understand what is going on, but at least being a theoretical physicist I could understand this is the part where this trap is present, and then the lasers you can see in front that coming from the 6 directions, at least one can get the idea. So okay, so these are the room temperature rubidium is a cloud of atoms, then magnetic trap, lasers are coming, and this is schematic diagrams, then evaporating cooling which is that what is done is the atoms, high energy atoms are taken out of the system, and then you have only left with the low energy atoms, and thereby cooling the system in nanokelvin temperature. So these are the basic, this is the basic step for the laser cooling, because laser cooling is very important, because you can take the system up to the microkelvin just by using the laser cooling in this system. And I must mention that I have given the example of all the alkali metal atoms, and these atoms are feasible for the laser transitions, and that was the main benefit of taking this sample. There are 2 reasons. One reason was that this if you cool the other kind of gas in reality up to the microkelvin temperature, it goes to either liquid or solid, but in alkali metal gas of very low density, and if you have seen, if you remember, the density is 10 to the power 13, and our air atmosphere density is 10 to the power 19. So it is very low density system. Although it is low density, it is confined in a very localized space, and moreover these atoms are transitions are in the optical range. You can do it with lasers. So that is the main advantage of these, and so laser cooling would be the most important part to start with, and this utilizes the Doppler shift. And I would like to mention that this is the frequency, like it is the lasers are applied from 6 different directions, and atoms are moving randomly. Now what is happening? Now this is the frequency what this atom sees, and this is the actual frequency of the laser, and you see that nu is less than nu 0. So the frequency seen by the atom is less than the actual frequency, and if the observer approaching the light source, like the light source and the atoms are coming opposite way, and then this frequency seen by the atom is more than the actual frequency of the laser. So what can be done is, in the experiment, nu 0 is the frequency which is matching exactly the level difference of the atoms. Now in experiment they have lowered the frequency little bit lower than this nu 0. So when the atom is in motion in the opposite direction, have the relative velocity, positive relative velocity, then it will see the frequency which is exactly equal to the nu 0, but actual frequency is less than that. So then it absorbs the laser. Okay, so although the frequency is little lower than the frequency of the difference between the energy level, but still it absorbs the laser, because it sees little bit more frequency because of the Doppler shift. So turning the laser frequency a little bit lower than nu 0, the laser beam opposing the atom is Doppler shifted to absorb the photons. So atom is actually absorbing the photons which is having the frequency little lower, but when it emits the photon, it will have the frequency which is nu 0. So the absorbing photons less than nu 0 and emitting photons which is nu 0. So it is emitting photons of energy which is higher than the absorbed photons. So it is emitting more energy than it is absorbed. Okay, so that is why this is the reason of the cooling down the system. So it is emitting the energy more, absorbing less. So that is the reason of having the cooling due to the Doppler shift. But the difficult part here in the experiment, this is very easy in theory, but it's not very easy in experiment. So what is done is, if the temperature is getting lowered, then you have the change in nu 0 the frequency available in the system. So you have to continuously tune the laser very precisely to match up with the again and again lower frequency. So that is the very difficult part. So laser frequency must have to be continuously tuned. But anyway, this is done with the laser cooling, and it can go up to the microkelvin. The next step is the optical molasses or magnetic trap. So basically optical and magnetic field both can be applied to the system to trap the atoms in the middle, and the last step must be the evaporating cooling. So it is very simple in the mechanical system like the cup of tea, but it is not very easy in the experiment. So what is done is in the magnetic field, when the spins of the atoms are aligned, so they are attracted towards the center of the field. So they are attracted towards the minimum of the field, magnetic field. But if they are not anti-aligned, if they are in the other directions, so they are repelled from the field. So that is the reason of this thing. So they basically change the magnetic field in such a way using the radio frequency, and they flip the spin of the higher energy atoms. When they flip the spin of the higher energy atoms, they repel from the field and they go away from the system. That is what is seen, that you see the higher energy atoms are there in the upper portion and they are going away from the system. So in that way you can see that it is changing the spin and it is getting the force which is taking it out. And in the other way you can also see that the potential is changing, because anyway you are using the radio frequency, so that is changing the potential and taking the atoms away from the system, which is the red atoms of higher energy atoms. And that is the essence of evaporating cooling. So here I would like to, this is a simulation by this Cornell and Wyman group, and this is, you see that this is 400 nanokelvin, 250. So with lowering the temperature, this is the critical temperature. So suddenly the atoms density is very high in the middle, and that is the point of Bose-Einstein condensate. So basically you have a large number of atoms present in the system. So this is plotted in the momentum space. So here in this system, this is the simulation. You see this is the temperature it is lowered. When it crossing this is the critical temperature, and when it is crossing the critical temperature, it shows sudden jump in the density. So when it is crossing it, and then there is jump. So that is the point of BEC. And also I would like to mention that if you see the critical temperature, it is also going down. So the reason is that I already mentioned this relation before. There is a relation between the atomic numbers and the critical temperature, because if you have the systems, this is a very dilute system and trapped in a very critical way, so there will be some loss of atoms at the end of the experiment. So the system will be losing atoms with time, and so the temperature Tc is should go down. Okay, so that happens in the experiment. That is why it is going down. So, so this is the experiment, how it is done so far. Now I tell you, because this is more or less the basic of the experiment. So this is just to tell you that how it is measured. If I see some BC system in reality, and how to measure it. So this is normally measured in photo absorptions, is the absorption spectra they take. This is a experimental one. You see the red one is a maximum. And then this is the absorption spectra, is the percentage of absorption. In the middle it is very high, and this is the distance in micrometer, and you can see that the distance is almost 100 micrometers in the range in reality for this rubidium system. And this is the theoretical plot has given. So this is the absorption spectra, but there are other ways to observe it, like phase contrast imaging and other things, but this is normally well followed of this thing. So now so far I told you that so basically I will tell everything like theory and experiment side by side, so that you can get the flavor of it. And then this is the harmonic confinement, 3-dimensional x, y, z, and then energy is, this is well known, and then number of particles can be found with the distributions. There will be some occupation number here. So but there, so this is the number you can calculate. One can calculate with a particular kind of this harmonic confinement and find the critical temperature out of it. So if one needs all the frequencies is well known, then one can really find what is the critical temperature. So this is the wave function, and in experiment you see that we have shown you that the distribution function and the condensate fraction below critical temperature it rises up and goes to 1 at absolute 0. It is exactly, these dots are all experimental point, this is exactly following, and this is condensate atom in the middle, and there is some thermal cloud. If you remember the movie, there are some yellow clouds in the background, and that is a thermal cloud, because there will be some atoms which is not condensed. Okay, this is still in the system, but it is not yet condensed. So those are the things is called the thermal cloud. Okay, so just I will not go into details because I do not have time, because I also give some research outline in this area. So this is the atom-atom interaction which is done analytically, and at the end for the low energy one can approximate this to the AS wave scattering. So basically the scattering length we will be talking about is mainly AS wave scattering length, and this is how it is done. This is the scattering plots, but here I would like to mention that the scattering length we denote by A, and for ideal gas we do not have any scattering, so we neglect the interaction between the atoms. So basically this scattering, if we consider the repulsive interaction between the atom repels each other, because this depends on the system to system. If you consider rubidium, if you consider lithium, it changes. So for the repulsive system, you see that this is the original ideal gas and the density is lowered. So there will be a deficiency of atoms in the systems because of repulsive interaction. Reason is that atoms are repelling each other, and so though they are going away from the center, and so the density in the middle is getting lower. And this is an attractive case which is A is negative, where you can see that this is the actual BEC ideal gas, the density is higher than the ideal situation. So this is the attractive case, this is repulsive, and this is, I would like to mention for the one dimensional gas, I will explain in detail what is the meaning of that. In that case is a very famous thing which is the soliton, which is the excitations obtained in the nonlinear systems, and I will explain in more details that is obtained in one dimension. So now let us see that after explaining the BEC and how to find the parameters, like in experiment we have seen how the things are done. In theory also one can calculate exactly what is the parameter. So let us now see that what is the dynamics of BEC. So the theoretical background of this is this. So basically we will use the second quantized Hamiltonian using the Bose field operators, and here is the single particle Hamiltonian. This V is nothing but the external potential we are talking about. Like in 3-dimensional harmonic oscillator or so, this is the potential which is responsible for that, and this V R prime, don't confuse these two potentials. These are the interaction potential between the atoms. These are the atomic interactions in the system, and this is the external potential. So by taking this AS wave scattering length approximations, one can get the Hamiltonian like this. So and then using the Bose commutation relations and Heisenberg equation, and one can say that this is the mean field part. Mean field part means basically we are considering that these systems are very dilute, and is a many body system. There is no point of solving Schrodinger equations individually, is not possible. So what we do is atomic interactions are very short range interaction compared to the dimension of the cloud. So this can be treated as fluctuations, and this is basically thermal part here, but everything is inbuilt in the mean field part, which is a wave function of the condensate. So if one derives this one can get the equation for psi, and this equation is the dynamical equation in 3-dimensional equation is called the Gross-Witowski equation, which is very famous equations and is a 3-dimensional equation, and there is no analytical solution of this equation so far in the literature. So as you can see that this is almost the Schrodinger equation, except the nonlinear term is introduced due to the atom-atom interaction in the system. So it is very non-trivial to solve this kind of systems, because to exactly solve what will be the form of psi, it is very difficult. So let us see that how it can be solved exactly. What are the ways one can treat this system to solve it exactly. So this is the Shigar shaped condensate. Shigar shape means it is a kind of one-dimensional confinement, and you can see that is a transverse dimension and the axial dimension. Transverse dimension is very less than the axial one. So basically you have a linear dimension of the cloud, and where you have a very tight confinement from the transverse direction, and the longitudinal direction you do not have any confinement, or you can have a very weak confinement in that direction. So in that way you can find a almost quasi one-dimensional system in reality, and this is not only theory, this is well realized in experiments. All the experiments, most of them are in one-dimensional scenario. So under the condition transverse dimension of the cloud is small, the corresponding time scale is sufficiently rapid. So basically the transverse cloud is calculated and taken out of the system, and then only you are left out with the longitudinal part, which will be your dynamical equation, and then you can solve the longitudinal part in some particular directions. Here it is z direction. So so that is the thing. So this is the equation which is 3 dimension. What we do, this is a cylindrical harmonic confinement, and then this kind of confinement we have to consider atom-atom interaction. So what kind of atom-atom interaction we should consider? So we can have 2 domain, weak interaction and strong interaction. Okay. So in this case, let us see that what are the dynamical equations if we take this kind of limit. So let us see, these are the 2 equations which is the one-dimensional dynamical equation in this system. And the first one is for the weakly coupled. If the atom-atom interaction is not very large, is very weak interaction, then we can have the one-dimensional equation. You see that this is only dependent on z and time. Okay, and this is the nonlinear part, which is written sigma is the density, and this is the scattering length, which is responsible for the interaction between the atoms. And for the strongly interacting regime, this is a different time. So now these systems are solved. The group of Professor Panigrai and we have solved it in the way to find the solitons. So here I just say that the experiment by solitons, finding the first experiment to get the soliton in this system, the same theory I am explaining, the same experiments, which is by this trap, the cylindrical harmonic trap will create the soliton. By using the phase-back resonance, they change the scattering length. So if you phase-back resonance is the method that you change the magnetic field, and by that you change the scattering length, and by that you create the soliton in one dimension. And you see the picture is not very high resolution because it's taken from the paper, and you see the solitons are propagating with time. Solitons are propagating with time, and the nature of the soliton is, the property is that it is a self-similar solution. Self-similar means it propagates with time almost without decay. So that's the property of the soliton. So it propagates a long time. You can see that 2 millisecond, 6 millisecond, and 8 millisecond, and so on. So they have found the soliton up to long time to have the similar kind of shape in experiments. So so now let us see the 2 domain, 2 equation. So we solve it like I just don't give the I will not make you bored by giving the all these calculations. So these are the basically the trajectory we get of the density. So this is solved by taking the help of the elliptic equation and all, and this is the case for the weakly coupled case. So if the atom-atom interaction is not very strong, is a weak interaction, then we can have a soliton of this kind. And if we have the strong interaction, you see that this profile is very, very different. And this is kind of profile which is not a bright excitations, like we do not have a atoms in the center, which is the elevation of atoms. We have the depression of the atoms. So if it is touching the 0 at the middle, then we call it a dark excitation or dark soliton, and here it is a bright soliton. So it is not exactly dark because here it is a shape is different. It's a kind of W kind, so we call it W soliton in this case. And so let us see that what happens to this soliton if I take the parameters time dependent. So basically now I enter into the domain of coherent control, and when these parameters are all time dependent. So far I have not taken the trap. This is just the example of how to solve this equation by fractional transform and elliptic equations and all. And here I like to consider the time dependence. So here you see this is the trap in the z direction. So in the directions of our interest is having some trap which is a harmonic kind, but the frequency is time dependent. Here the scattering length, which is gamma t, which is the result of atom-atom interaction, which is also time dependent, and this is the factor which is imaginary, which is basically responsible for loss of atoms with time. So this is the equation which is a very general equation. So how to solve this general equation? So this is some steps where we have taken the answers and some traveling coordinate, which will be some center of mass motion will be contributing here LT, and that can be also found. So basically once we know the oscillator trap, what is the MT, so basically that should be supplied to the system, because if you have the experiment in reality, you know what kind of trap you are using. So you know the beforehand you have the information of MT, and then you can put it in the all the terms, like I have not given all the expressions, so you can find what is AT and BT and all these things. So this is the wave function of the condensate, and this is the density part, and you can exactly find what is the profile for BEC. So even for the time dependent case, it is not impossible to find a exact solution of this system. So basically this is a time dependent scenario, so that you can see that what is happening with time for the BEC. Okay, so this is still continuing, because this is a nonlinear equations, we solve it, consistency equations and all. Okay, so now let us see that okay, so after having these things, one can have various kind of plots in various kinds of trap and frequencies and all. So this is a family of solution, is a very general solution, one can have different kind of applications. So that's a different context, but I will quickly go to the main goal. So this is a wing interactive, just one example that this is the experiment by Strecker et al. In 2002, that they have observed the multi-soliton trains. So there are many solitons in the system, which is they are oscillating in the trap. So this is the domain of the trap, they are oscillating, but at the edge of the trap they are very nearby, but the middle of the trap they are away from each other. So the similar thing, it is not very well, as the resolution is very less, we can have the similar situation from the coherent control. We can have the oscillatory solutions, have the Gaussian smoothing, and then we can have the similar kind of thing. This is distance of the soliton is more, and then it is coming nearby in the edge of the turning point of oscillation. So this is the thing for the strongly interacting regime, where you have the strongly interacting regime. If you remember that we have taken the time dependent part, and the soliton is the kind of thing we have obtained this, which was the time independent case. Now for the time dependent case, so this is at t coordinate, t equals to 0. So you can see that this is a kind of W. This is the same profile to start with. So this is a W kind of profile, and then this W profile is oscillating like this, and this oscillation you can see from here. So this is a W profile which is oscillating inside the trap, because you have a confined trap in the system, and this is the profile which is again, it is a W density profile oscillating in the trap, but you have a loss in the system. So if you have different kind of loss, you can have the treatment for that. But here we have just taken, for example, some oscillatory decaying trap here and there. So we can have, just for example, we have taken like this. So this is a coherent control of W kind of soliton in this system. So let us see that after saying this, that now you are familiar with solitons and how this can be coherently controlled in the system. So let us see that how this quantum information comes into picture. So this is a quantum system, and this is a coherent atomic system, because you see that all the atoms are in the single quantum state. So they are having the same phase. So it is a coherent atomic system and have long range correlations. So that is why it is very appropriate for observing the quantum information structure in this system. It has direct implications of the atom lasers and Josephson effect for atoms, because in lasers we have the coherent excitations, coherent emission of photons, all are having the coherent phase relation. So here also in atoms we are having the similar kind of thing. The only thing is that we have to think about the lifetime and the number of atoms in the system. That's the difficult part in experiment. So BoseEinstein condensate of longer coherence time is a promising candidate for observing mesoscopic superpositions. So once we have this kind of solitons in the system, we can have superpositions, and we can have a lot of quantum information science out of it. And this offers the matter of interferometry, what are the lasers or optical interferometry. So I will tell you the experiments, in very recent experiments in this literature. So this is a science in 1997. This is the first observation of quantum information in Bose-Einstein condensate. So you can see that this is done in double well potential. The potential I have been talking about is a harmonic well so far, but here if one takes the double well potential, then what happens? So they create the BEC in both the well. So there are two wells like this. They create BEC here, they create BEC here, and that is why you can see that the BECs are splitted. Here one well, there another well, and then they can change the distance between the well. So by changing that, you see the distance between the BEC is increasing. So now at the end of that, they release the trap. So they switch off the laser beam, and then there is no trap. So the BEC was there, now I switch off the laser beam. So after that they recombine and they form the interference structure. So this is a very clear signature of interference. You can see this is a kind of hyperbola they have given, which is for the very short distance between the BEC, and this is for larger distance. And this is the absorption imaging I have mentioned. You can see that this is one BEC and this is another BEC. In the middle you have a very oscillating ripples, which is the signature of the interference structure. And like that they have found it, and they have found the fringe period and everything in terms of the physical parameters. The observation of high contrast interference fringes is clear evidence of spatial coherence over the extent of condensation. So this was the first experiment, and this is a very interesting one, is very recent recent paper where they have done very cleverly that this is a double well profile. Now they don't create the BEC in two wells, they create the BEC in single well, and then they lower the barrier of the potential. So what will happen, the condensate will go from one to another, it will tunnel from one to another, and then it is going to the another. Now it raises the barrier, so then two BECs are separated out. Okay, so this is very good idea, in the sense that you have the same atoms and you are dividing it, so you have a coherent superpositions, and then you lower it again. When you lower it, then they superpose each other and they find the interference structure. So, and this is the work which is the atomic interferometry. This is another remarkable thing in 2004, where they have used the acousto-optical modulator and use a beam, laser, the atomic beam, and they pass through a lens and then focus it, and so by that they create the double well, and they convert the single well to double well basically. So initially they have the single well here, you have the double well here. So you see that the well is from single well to double well, it is slowly becoming double well, and that is why this is the clear signature of beam splitter. In optics, what is the role of beam splitter? If you have the incident beam and then use the beam splitter, then it splits into two parts, and that is happened for the laser. And these are similar kind of thing done for atoms, because they are coherent atoms. And once you do the beam splitter experiment with atoms, you have lot of freedoms to do the quantum interferometry in this system. So this is the signature of interference if you release the trap. But this is the main point, is they have used it as beam splitter. So this is another very good experiments, which is the Nature Physics in 2005, which is you can control the depth of the well, so that the density of the well you can control, and so that you can control the interference structure. So controlling interference structure has a lot of implications in metrology, in quantum communications. So this is very important in that sense. And this is a very recent one, is twin atom beams in Nature in 2011. So what they do is very beautiful experiment. This is they create the BEC in the higher excited state and two BEC in double well, and then they take it to the ground state suddenly, very fast adiabatic process, and then you can see here that two atomic clouds, they are going far apart with some momentum. So this atomic cloud, two BECs are having the momentum, they are going away from the momentum when they release the trap. So what you get from the system, you have the two coherent beam coming out. So that is basically twin atom beams, which is a very remarkable thing in atom optics, because in laser this is very useful thing for quantum communications and many reasons, entanglement and many reasons, correlations. So here they have produced these twin atom beams in this experiment. So let us just see that what is our proposal for create and control of quantum interference. I will just give the idea of that. So first point is that using the W type soliton, if you remember, in strongly interacting regime we have found that, and we have also studied in coherent control, and there are two dips, okay, like one depression of atoms, another depression atoms, and if you can create the interference between the elevation of atoms, you can also create between the depression atoms. So that will be, the fringes will be opposite. So that's one proposal, but that we have to do it. And the second one is bright soliton trains, which is experimentally observed systems. We are utilizing that. And then there is some model using the double well configuration. The examples of the experiments I have given, we can exactly do it in theory, and there is no theory in general, and there is two component BEC in time varying scenario. So this is the first case one can do in coherent control. One can observe experiments between the BEC of these two positions. And here is the bright soliton trains, which is the experiment in 2002, they have observed the multi-soliton trains, which I already mentioned. So this can be modeled by two soliton dynamics. So if you observe two soliton dynamics with time, and we model it like this, and then they oscillate, each solitons oscillate, and every time when you release the trap, you have the quantum interference. But you have a control of the interference each time, because you have the distance of the BEC, or the distance of the mesoscopic states different with time. So what is happening is we have this kind of structures. If you have, so basically what we do, that you have two BEC, we have a overall phase between BEC, so you can change the BEC, overall BEC, you can translate in space, and also you have an overall relative phase which will make it rotated in space. So basically the system is in this way. This is just a diagram. So this is a two, it will be generated like this, and if you have a relative phase in the system, you can do it like this. So if you change the phase or the momentum of one soliton with some perturbation from the outside, like I change this momentum of this soliton with any perturbation from the outside, then that can be measured using these interference structures, because the interference structure will change as this is very small structures, this will be very sensitive, and one can measure by evaluating the overlap. And this is I think the main focus of our result is that this is the equation, is very general equation. You can see that all the parameters are xt, xt and xt, all are space and time dependent. Why we do that? Because while doing the double well interferometer, this is the most recent progress in this area, because quantum interference and these quantum communications. So you have to have a space dependence density, and also the control of space, control with space, so that you can control the well. So that is the reason of taking this kind of thing. So we have started, like, we have not taken any form of the potential here, and then we are taking the answers of this kind, and this is a very non-trivial calculation, as work is still going on, and we have a traveling coordinate, this is the amplitude, and you see that these functions are all, you can take any form of this function depending on the requirement. So this is still a general thing, and this is the phase, and this is the potential expression for the potential. So once you do not need to take any form of the potential since the beginning, because you can have a solution for many potentials. So this is a very powerful result in that sense, that you can model many systems out of it. But we will just mention that how we can model the double well kind of scenario. So this is the total solution of the system, where it is done for the attractive interaction, and this is AX and BT, all these terms will be responsible for how you are manipulating, how you are controlling the system. And this is general solution of the system, which involves a family of solutions depending on the form of different analytical functions like AT, BX and all these things. These functions can be chosen according to the appropriate modeling of the particular process. So you remember the experiments I have described in double well. First they have realized these in two well, then single well, then changing the parameters, then tuning the depth of the well, and all these things, everything can be done with this. So double well potential is one of the outcome of our study, where the positions and potential minima, barrier height, asymmetricity can be controlled. So you can basically change this function BT to change the depth of the well, and you can change the function AX to change the barrier height and the position of the well. So like this, you have a lot of freedom in this system to change the potential, and accordingly you will find what is the density profile of the system. So you can model basically all the experiments of this kind using this theoretical result. So I can say that this is a double well potential with tunable barrier. This is the maximum control possible of the quantum interference structure in Bose-Einstein condensate. So this is our main result. So basically what we have done is I started from the very basic, and I will just summarize in a minute, and then how to find the exact solutions in this system which is consistent with the experiment, and solitons, and then how they propagate with time. That is called the general coherent control. And then there are experiments in reality, which is the interference and manipulating interference, control of interference, and that can be modeled with this last result, which is very general in reality. So I end up with this thing, and thank you all.